We present LXM, a family of algorithms for pseudorandom number generation. In this talk, we give background for the problem and explain some of the prior art, then present the algorithm itself in one slide, now that we have set the context. Then we discuss some of the properties of the algorithm, and then present the specific contributions of our paper. Pseudorandom number generators have been around for about 7 decades now. Back in the 1960s, what we typically wanted was a stream of floating point values drawn uniformly from the range 0 to 1. And this is approximated by drawing uniformly from a set of specific values. You would generate an integer between 0 and p, and then divide by p. And it was considered okay if the low order bits were not very random because they would end up in the low order part of the floating point significand. Nowadays, we still want to be able to generate that kind of floating point value drawn uniformly from 0 to 1. But we typically expect the value p to be much, much larger. In addition, we would also like to be able to extract a stream of w-bit integers drawn uniformly from the w-bit integers 0 to 2 to the w minus 1. And we expect all bits of each integer to be equally random because these integers may be put to various purposes, as bit strings, to take the remainder where it matters that the low order bits be as random as the upper bits. And so there are different applications. We want all the bits to be good. Other things have also changed over the years to change the nature of the problem of pseudorandom number generation. Moore's law, for about 40 years, made computers ever faster, and as a result, nowadays applications can draw many more numbers in the course of their execution. So a pseudorandom number generator that repeats its sequence after generating only 2 to the 32 values is not considered okay anymore. Furthermore, the test suites used to verify the statistical properties of pseudorandom number generators have become much more discriminating. Nowadays, we routinely test trillions of generated values rather than just millions, looking for subtle statistical anomalies. This has improved the quality of the PRNGs, but has also made them harder to design. In addition, computers now have a lot of parallelism of various kinds, either SIMD or multithreading. And so we want to be able to run just not one pseudorandom number generator, but perhaps dozens or millions of them simultaneously, and we need them to behave as if statistically independent. Here is a model of the basic structure of a pseudorandom number generator. There is a state, which we can think of as residing in a register or a variable, and at every tick of the clock, the value of the state is run through a state transition function, and the new value is then stored back into the state. In addition, that new computed value is put through an additional output function, and the results of the output function is a stream of values, one at each tick of the clock. To describe it a little bit more mathematically, we will call the initial state S0, and for every tick of the clock, S sub k is computed by applying the transition function f to S sub k minus 1. And so we're constantly producing a new stream of states, S1, S2, S3. The output function g is applied to each of these state values, resulting in a stream of values t sub k, producing t sub 1, t sub 2, and t sub 3. We assume the function f is bijective, and as a result, the sequence of states is a cycle. And the smallest k for which S sub k equals S sub 0 is called the period of the generator. This is the total length of the circular sequence of states. On this slide, we make a slight adjustment to the algorithm. It's kind of an engineering hack. Rather than taking the output of f and feeding that as the input to g, instead g takes the state directly. This is a trick that allows f and g to be computed in parallel. As a result, g computes a sequence of values t0, t1, t2, rather than t1, t2, t3. But it doesn't matter because the overall sequence of states is a cycle. Now we look at a specific example that has been widely used, a linear congruential PNG with a prime modulus. So given an integer state s, a modulus p, and a multiplier m, the update function multiplies s by m, takes the result mod p and stores it back. The output function divides by p, and this gives a sequence of values between 0 and 1. In fact, they will all be non-zero. The reason is we must choose a non-zero initial state, or else all of the produced values will be 0. It's also important to choose p and m carefully. Typically, the modulus p is a prime. One drawback of this specific algorithm is that that is a floating point division in the output function, and division tends to be expensive. An alternative more suited to modern requirements is a linear congruential generator with using a power of 2 modulus. We use k bits of state, use a modulus 2 to the k, and the multiplier m must be odd. The output function, instead of requiring a floating point divide, simply retains the high W bits of the K bits of state to produce a W bit output. This is much faster than floating point division, and converting the resulting bit string to a floating point number is also reasonably fast. This is a pretty good generator when K is at least twice W. But when K equals W, the low order bits tend to have small period. In fact, the lowest order bit is always a 1. The overall period cannot be larger than 2 to the K minus 2. A further improvement to this strategy is to introduce an additive parameter A, which must be odd, and require the multiplier mod 8 to be equal to 5. With this set of constraints, the period will be fully 2 to the K. Every possible W bit value can be generated. Every possible K bit state can be generated. When K equals W, all 2 to the W possible values can be generated, and therefore we say that this generator is exactly equidistributed. But the low order bits still have low period. The lowest order bit has a period of 2. It alternates between 0 and 1. The next bit has a period of 4, 0, 0, 1, 1. The next period has a period of 8, and so on. The introduction of this additive parameter A suggests an interesting idea. Can we use this parameter to provide for independent parallel streams to be used by multithreaded or SIMD operations? The idea would be to create many instances of the algorithm, each with its own state S and with a different value for A, and then each parallel thread would use its own instance. Versions of the algorithm without an additive parameter have also been used for multithreading. The idea is simply to have one big state cycle, as shown here on the left, and have the different threads, shown here as T1 through T4, traverse different parts of the state cycle. It's important to initialize the states for the threads so they will traverse different parts of the state cycle so they won't get accidental statistical correlations. The idea on the right is for each thread to have its own state cycle, which could be smaller. But if each of these individual cycles behaves as if statistically independent of the others, then in effect, all these threads can use the same algorithm. And the question is, can the parameter A be used to provide different cycles? It turns out that the answer to this question is no. This is not a good idea. There's a theorem that if you have 2 instances of this algorithm, one with additive parameter A and one with A prime, for any choice of A and A prime, you can find constants I and R, such that in effect the state cycle of one is equal to the other one offset by I positions, and then having the value R added to it mod 2 to the K. In visual terms, changing A doesn't change the shape of the graph that plots T sub j versus j. It only translates it both in time and then vertically on the graph modulo 2 to the K. This theorem allows us to show an equivalence between 2 different algebraic structures. The upper one is the linear congruential generator that we've already seen with the additive parameter A. The one at the bottom replaces A with a constant 1. It introduces a value R that is added in to the output just before the high bits are kept. If R is chosen appropriately as a function of A, then these 2 generators produce the exact same cycle of values. But there is an additional improvement we can make that makes this idea work out pretty well after all. After the linear congruential generator, we add an additional hash function to the output function. Think of this hash function as a bit mixer. Ideally, it has good avalanche statistics so that whenever any bit that comes into it is changed, half of the output bits tend to change. This generator works pretty well for parallel threads, and it solves the problem of low period bits because it allows the high period upper bits to affect the low period bits through the use of the hash function. But the period is still only 2 to the K. If we want to have a generator with a very large period, we need to make the state larger. Unfortunately, then the multiplication operation in the linear congruential algorithm becomes expensive because it has quadratic cost. An alternate approach is to use an F2 linear or XOR-based generator. Here the state is treated as a vector of n bits, and the update function multiplies it by a fixed n by n bit matrix. The overall period can be as large as 2 to the n minus 1. In this case, again, the state cannot be all 0, or else the outputs would all be zeros. A feature of this is that the output is n over w equidistributed. That is, if n over w is 2 or 3 or 4, then 2 tuples or 3 tuples or 4 tuples generated by the generator are equidistributed. Furthermore, we can choose the bit matrix carefully so that instead of having quadratic time execution, it has constant time execution using a fixed series of w-bit shift, rotate, and XOR instructions. The statistical properties of the output of an F2 linear generator is also not perfect, but this can be considerably improved by the same trick of adding a hash function onto the output. The statistical deficiencies of both the linear congruential algorithm and the F2 linear algorithm can be ameliorated by combining them into a compound PRNG algorithm by using one instance of each and then summing their outputs. Both Marsalia and Lecuyer and Granger-Pichet have studied such compound generators in detail. One advantage is that the overall period is the product of their individual periods, because the period of the linear congruential generator is a power of 2, and the period of the XOR-based generator is odd. An additional advantage of these generators is that they are equidistributed. Their output is still slightly weak, but as Marsalia commented, if the numbers produced are not random, they are at least higgledy-piggledy. And now, ta-da! With all of that as background, we can show you the diagram for the LXM algorithm presented in our paper. It is a simple combination of elements we've already seen. There is a linear congruential generator, an XOR-based generator. Those results are summed, and then the result is run through a hash function, also known as the mixer. And it is our thesis that this compound generator with a hash function added will successfully solve many of the problems that we faced heretofore. A Java implementation of this algorithm has already been deployed in JDK 17, and this is part of a larger API design that includes a new random generator interface, which we expect to make it easier for new PRNG algorithms to be created, and also to make it easier for applications to switch among PRNG algorithms. In addition to members of the LXM family of algorithms, this JDK 17 update also includes versions of the XOR-based algorithms Zoroshiro and Zoshiro. But wait, the title of our paper promises that this algorithm is splittable. What does that mean? The idea is that given one instance of your algorithm, you can dynamically create the state for a new one that is statistically independent. This is a generalization of the well-known idea of jumping to a randomly chosen point within a single state cycle. This idea appeared in the SplitMix algorithm presented 7 years ago at UPSLA. The idea was just to generate the new state data at random. But this approach was derived methodically by stepwise refinement of an earlier algorithm called .mix from 2012. But not all states for the SplitMix algorithm work equally well, so it's necessary to reject certain state configurations that are known to be weak. This is deployed as the Java class Splittable Random in JDK 8. Unfortunately, other configurations also turned out to be weak. See this paper for an explanation of why. LXM uses the same approach by splitting new instances, creating their states at random, but we have good theoretical and empirical reasons to believe that LXM does not have any weak configurations. We could be wrong, but this is the hope. Other strengths of the LXM algorithm stem from its specific combination of components. Thanks to the linear congruential generator, the W-bit results are exactly equidistributed. The additive parameter A makes it easy to provide independent parallel streams. And the LCG greatly improves the tuple equidistribution of the XPG. Thanks to that XOR-based generator, the period can be made very large without a large speed penalty. And if the XPG produces equidistributed tuples of a specific length, so does LXM, only better. The mixing function eliminates linear artifacts, particularly the low period, low order bits. And the mixing function is crucial to producing independent parallel streams. In effect, the additive parameter of the LCG selects a specific variant of the hash function provided by the mixing function. LXM is a simple, even incremental idea, but apparently not in the prior literature. We've seen many combinations of 2 of these elements before, but not all 3. To conclude, the contributions of this paper are explanations of why these specific components were chosen and why we combined them in a specific way, analysis of certain properties of this combination, including the period, equidistribution, and probability of accidental correlations. We provide a comparison of this algebraic structure to a great deal of prior work. We did extensive quality testing using the TestU01 and PractRan test suites, and these test results are reported in the paper. We did studies of scaling, testing up to 2 to the 24th parallel streams using various splitting strategies, and also testing very small versions of the algorithm using as little as 48 bits of state. Finally, we conducted timing tests that demonstrate that LXM is indeed almost as fast as SplitMix. Thank you for your attention.